Chapter 5 is going to bring back a level of comfort to you in some ways. The counting stuff is hard. Okay? But I think it helped us kind of wrap up Chapter 4. I think that was a good thing to do. Chapter 5, we say, okay, now you understand probability a little better, we hope. But I think that if you learn what random variables are, that's when you really get to understand probability and then how it's going to be related to statistics, why they're related. So, I will talk about a random variable here. So random variables, we know what variables are. These are variables that can take on values relevant to a problem, let's say. Relevant to a problem. You know, in the last example I had, I wrote down a random variable x, and I said it can take on certain values. Do you remember what values it could take on? 0, 1, 2, or 3. Now, I want to bring back two words that you saw before. Discrete and continuous. Remember these words? We were talking about data, and we said data can be discrete or data can be continuous. Numerical data, that is. I'm going to tell you that random variables can be discrete or continuous. Is that okay? Random variables can be discrete. Random variables can be continuous. In the example we just did, where the x represented the number of women, where do I lump that? What's that an example of? A discrete random variable or a continuous random variable? How do you know that when I say x is the number of women on the committee, how do you know that's discrete? Yeah, you're not going to have 2.5 women on the committee. It's not if you're polite. All right, so let's see. Number of women on the committee. Civilized? All right, continuous. Can someone give me an example of a random variable, I'll call it y, which would be a continuous random variable? Y has to take on a value that is relevant to some problem. So, like what?
Like a point, anything positive, it can just go down and never ends.
Yeah, boy, that's very abstract to me. I mean, you may be right. What was this? Temperature? So, could it be that you might want to measure a temperature? We would say y is the temperature where? Let's make this a real example. In Cleveland. Is that continuous? Why? You could have 70.4 degrees, right? Or 70.3 degrees, or 70.35 degrees. You could have any number you could think of, although you might not be able to accurately measure it after some point, right? But if you can do anything, that's continuous, right? Kate, you mentioned infinity, and I do want to come back to that because we can have infinite, this is very interesting. You could have a possibility where your random variable could become infinite, and it may be discrete, or it may be continuous. How's that is a good question. Well, let me give you an example to make it real hands-on. Let's say I do this. Suppose x is the number of times I flip a coin let's see, how do I want to say this? Let me do it better this way. Suppose I flip a coin. If I get heads, I flip again. I repeat this process until what? Until I get tails. Okay. Let x be the number of heads we get. So what values could x take on? It could take on 0, right? You might flip tails right away. Or 1, or 2. Could you get x equals 120? Is that likely? No. But could you? Could you flip 120 heads in a row? Possibly. Could you get 100,000 heads in a row? Possibly. I mean, you'd start to say something about the coin. We mentioned this, right? So here's the last question I have before I take a next question. Is x discrete or continuous? X is discrete. Even though there's no limit on how high x can go, that's not what makes it discrete or continuous. Why is it discrete? You can't get 2.5 heads here, okay? You see what I'm saying? It's discrete. Okay. Now, we need to understand this because our rule for probability is going to be a little bit strange. See, I might ask questions like, what's the probability that x is less than or equal to... no, let me do it this way. Probability that x is bigger than or equal to 2. I might ask that. We're not going to solve that today, but we will some point. What's the probability that I'm going to flip and I'm going to get x, what does that mean? X bigger than or equal to 2. What does that mean? You at least get heads twice before you get tails. What's the probability of that happening? By the way, do you think that would happen? It could happen. I don't know how likely it is. That's what we want to compute at some point, maybe. By the way, what would be the complement of x being bigger than or equal to 2? Yeah, less than 2. So the complement would be the probability that x is less than 2. And if x is less than 2, in this case, that's the same as the probability that x equals 0 or x equals 1, right? And so all you really have to do is figure out what's the probability that x is 0. Oh, that I know. What's the probability that x is 0, that you get no heads? 0.5. Half the time, you're going to flip tails right off the bat. Then you might say, what's the probability that x is 1? And we'll get to that. So you compute that. And then if you want to know what's the probability that x is bigger than or equal to 2, you would do 1 minus the probability that x is less than 2. Okay? So these are some of the ideas that you've been playing with. We'll get to that. Here. So here's the thing, guys. With a random variable, okay, with a random variable say X, we often associate what is called a probability. Here's a word you've seen before. Distribution. Now wait a minute. What was it we distributed before when we had a distribution? Well, okay, yeah, frequencies were a measure that we talked about. But what was it that was distributed? Data, right? The data. And, oh, right, I remember. Frequency distribution was a kind of chart you made. Remember that? And then if you wanted to represent it graphically, what was the kind of graph you made? Okay, so we are also going to talk about what is called a probability histogram. And you know what? You actually saw this before. That time we did the dice rolling on the calculator, those histograms that were coming up, I guess they were frequency distributions, and they were frequency histograms, but the probability histogram kind of tells you graphically what the theory says should happen. Okay? So now I do want to jump to the book's slides, because these are good for the graphics. Here. Right there we were. See, the probability histogram is very similar to a relative frequency histogram, but the vertical scale shows probabilities. So here it says, probability histogram for the number of Mexican-American jurors among 12 jurors. Now, I have no idea where this data is from. So, must be some example in your book you'll read about today that they're going to, you know, maybe they were in a certain state and they noticed that, oh, well, lots of the jurors have Mexican-American in their blood because of where they were located. Okay? So what was the probability that you get 10 jurors that are Mexican-American? Well, in this particular example, it looks like it was around a little less than 30% of the time they had 10. Around 10% of the time, or a little more than that, they had 8. You guys see that? By the way, this is a random variable situation. What do you think X would represent if I were doing a random variable for this slide? Number of what? Mexican Americans. That's exactly it. I could say for that example, if X is the number of Mexican American jurors, right? I could say that. And then I could say, oh, what values could X take on? Well, X could be 0. There might be no Mexican-American jurors. X could be 1, up to what? X equals 12. Is this continuous or discrete? This is discrete. And then what you can do is you can talk about the probability that X is 0, or the probability that X is 12, or the probability that X is 8. And instead of listing them all on a chart, which we did with relative frequency distributions, it's a lot nicer to just look at this picture again, a probability histogram. Does that make sense to people? Cool. The vertical scale doesn't show frequency anymore. Now it shows probabilities. Does that make sense to people? Okay. Oh, yeah. Before I do that, well, let's go ahead and keep it up there. There are some requirements if you want to be a probability distribution. there are two requirements, and here they are. But do we know how to read that? Maybe we do now. What's that sigma mean? Sum. If you add up what? All of the what? All the probabilities. They have to add up to 1. Remember when we did relative frequencies? We said, oh, if we add them all up, it has to be 100% of the data. Same idea here. If we add up all the probabilities, they have to add up to 1. If you don't have that, it's not a probability distribution. What's the second one say? Probabilities are always between what and what? We knew that. Well, your probability distribution P of x has to follow that rule also. So those are nice to know about. Oh, I'm out of time. Okay. I may have to modify homework again. That's fine. That's okay. I will try and post that for you guys. Do I have people's homework? If not, on your way out, make sure you throw it in here. Nice work today on the group work. You can keep that sheet. It may help you on the homework, actually. Okay, so go ahead and keep that sheet. See you guys next week. Throw them in there together. Thank you. You couldn't get any of them to come up? Where did you try to log on? At home? So when you click on the link, what happens?
Hey, did you have a coffee? Did you see what they have for lunch? Huh?
No, I didn't get a chance to play my computer.
You're excited. It's a surprise when you go down there.
Yeah, it is.
You want to try one here real quick?
What did you get last time that you were excited? Italian sauce?
I think I had some meatball sub. It's okay.
Sorry, anybody?
Yeah, I was just asking a quick question about the last one.
Yeah. Yeah, show me real quick. So section 5.2, we're going to learn about what are called random variables. Now, I mentioned these last time. I said they were variables that can take on values relevant to a problem. So let's see. Oh, I mentioned all this stuff last time. So I just put a little reminder slide up here for you. So what did we do last time? We did random variables. So like x could be the number of whatever, right? And then, so how about this? X could be the number that shows up when I roll a die. Because I did that example before. Okay. Now there's something called a probability distribution function. And your book has been labeling that P of x. Okay? And what this means is this gives us, it's a function that gives us the probability that the random variable takes on a certain value. Yes.
An example that would be like when we did the card game, like you got a jack and an ace.
Yes.
So
Yes, I mean,
is that the NCR and NPR formulas?
okay. The NCR and the NPR are formulas to help us count. Okay? we need to do some counting to come up with the probabilities, okay? But what this is something that gives you the probability. So let me show you how it's usually written. Usually it's written like this, more like the probability that x equals some number k. So for example, I'm doing the die roll up there. Let me do the probability that x equals 3. Well, when you roll a die, and this is a very simple example, when you roll a die, there's only one way of getting a 3. You need the 3 spots to show up, right? When you know. So it's a 1 in 6 chance. That's right. Now, last time, oh, by the way, I talked about continuous versus discrete. Is this continuous or discrete? Yeah, there's only six choices. And then the last time, I also talked about a probability histogram, right? And this was, okay, you show the probabilities off. So if I were to make a histogram for the example I was just talking about the die roll, it would look like this. 1, 2, 3, 4, 5, 6. What's the probability of any one of these happening? 1 out of 6, right? They're all the same. 1 out of 6. Of course, the maximum probability you can have is what? 1, right? But this would be 1 out of 6. And I remember the experiment we did in the beginning of the year. You guys were rolling one die, and eventually, over time, our histogram started to look like that. That's the law of large numbers that we learned about. But that should get closer and closer to looking like that. It didn't work with 2 dice. 2 dice, we got more of a bell shape, a normal distribution. Same with 3. Okay. I think this is the last thing I gave last time. The requirements for a probability distribution. What does this say? The sum of the, what are these? Probabilities has to equal 1. Let me go back and make sure we understand that. You guys, what's this probability? 1/6 plus a 6 plus a 6 plus a 6 plus a 6. We add them all up. What do we get? Okay, so that's good. And then the other thing is that the probabilities have to be between 0 and 1. And we had that also. So we have a probability distribution. Part of what you have to do sometimes on these exercises, and even on the homework that you did for today, it said, hey, is this a probability distribution or not? You had to check. So we'll do an example or two like that, so that I can show you what they were looking at. Oh, yeah. This I did not talk about. So I said, well, you guys are going to have to read. Good luck. And that's where I was worried. I said, well, let me talk about it. So what I did is I assigned a couple more problems on this for Thursday, okay, out of the same section. It's funny because we've had all these words before, right? Mean. That's mu, right? We've had that symbol before. Oh, did we? What was mean for us? Oh, yeah. X bar is the symbol for a sample mean. Some of you read or learned that mu is what kind of mean? Population mean. Do you guys know this letter mu? It's the Greek letter for M. That's why they do it for mean. Okay? Mu is mean. So mu is, it can be a population mean, but it can also be the mean of a probability distribution, which is the thing we're talking about now, where instead of frequencies, we have probabilities. Now, one thing that bothers people is, oh, and by the way, another thing you may have read about, in the section they talk about something called expected value. This is just another name for mean. But a lot of books will write this, and I think our book does too. That means the expected value of the random variable x, e of x. Is that okay? I don't know. So here's a good question. I like this question. I'll do it in green. What is mu, the mean, when I roll a die? What is mu when I roll a die? Well, let me do that work over here on the side. I'll do it in black. So what am I going to have to do? Yeah, Craig?
It says like,
Another question. Go ahead.
like it's the average.
Yeah.
It's kind of like adding up the football players' jerseys numbers and averaging it out. You know, we had a lot of questions.
You're thinking it.
It doesn't really, the data doesn't really matter. It's averaged out.
You're thinking it doesn't mean anything yet.
Yeah.
I want to show you that it does. Okay? I want to show you that it does. And so hopefully you'll see that by the end of class. Okay? So it says to do x times p of x and then add all those up. So I'm going to make a column, and you saw this actually in the book. X and p of x. Now when I roll a die, what are the possibilities for x? 1, 2, 3, 4, 5, 6. That's it, right? That's the only possibilities. What is the probability for each one of those? 1/6, 1/6, etc. Right? So over here, I'm going to make a column for x times p of x. And of course, you could do it on the calculator, but this is a small example that we don't need a calculator for. 1 times 1/6 is 2 times 1/6 is 2/6. 3 times 1/6 is 3/6. 4/6. 5/6. 6/6. And some of you are saying, should I simplify? Well, you could, but you don't want to. Because what's the next step going to be? We're going to add all those up, and so the common denominator is going to be 6. See that? So let's add 1 plus 2 plus 3 plus 4 plus 5 plus 6. 21. Nice job. Yes? No? Let's see. 10, 21. 21/6. So that's the mean. Yes? Oh, when you add fractions, right, the denominator stays the same, but what do? I add all those numerators, so I just added all those up. So what I did was I looked for 10s. I got the 6 and the 4. That was 10 right there, right? And then I looked for 5, 3, and 2. That adds up to 10. So I got 21. See, but now I do want to get the calculator out. What is 21/6? Is that interesting? What's the mean die roll? Mu is 3.5. Now, is it even possible to roll a 3.5? No. Although this is interesting. Say you roll one die and you roll another die. And then you start adding those together. When you roll 2 dice, bless you, what is the mean going to be? Well, what's 3.5 plus 3.5? 7, which we talked about. We talked about 7 being the average roll, in a sense, the mean roll. And that's what you compute. When you compute this thing called expected value, or mean, this is what you're computing. Now, wait a minute. When we did mean, we had a different formula. What was our formula for mean back in the day? What did we add up? We added up all the x's and then divided by, yeah. Of course, dividing by n, another way to say that is we multiplied by 1 over n, which is kind of what I did here. What was n here? 6. See that? So I'm really doing the same thing that I used to do. But I'm doing it with probabilities instead of with data. Juliet, you look sad. You all right? Or you started zoning. You okay? Okay. because this is important. I don't want you guys to get lost. Yes? Great.
So finding out the mu, so you mentioned saying there's like formula there on top.
It is the formula, yeah. You're saying the one that we used to do. It really is very similar. Matter of fact, we kind of did this chart thing when we were finding a mean of a frequency distribution. Do you guys remember that? Well, it's the same thing, except that now it's a probability distribution. You have to multiply these things together before you add. That's all. Okay? All right. There are some other stats they give you. We had variance before, right? How do you read this letter? What's that letter say? Oh, you guys don't know that Greek letter? That Greek letter there is also sigma, but it's lowercase. This sigma is capital. Why would they use sigma squared for variance? Because guess what sigma is going to stand for? Standard deviation. And you don't have to write all these down, and I probably wouldn't if I were you. They're in your book. I'll have them on a formula card next week if you need them. Right? Tuesday. Yeah. We're going to have a test on Tuesday. Yeah. So, these formulas are all here. Remembering them doesn't matter too much to me because it turns out that they're a lot like the old formulas. Remember how we used to do variance? How do we do variance? X minus the mean, square it, and then we used to add them all up and then divide by what? Divide by n or n minus 1, depending which kind it was. Well, now instead of doing the divided by n, we're kind of multiplying by each of the probabilities. And I'll show you that as we get into it. Okay. Yeah, in problem 12, they give me some nice data there. I'm going to go ahead and use my grafting calculator for this. I want to enter that data into the calculator. Remember what I press? Press the stat button. We want to edit a list. I'm hoping I can go quicker now, but I want to make sure you're with me, okay? So you press the stat button, and then you press enter to edit a list. Oh boy, I have all kinds of lists I don't want. For example, if I want to get rid of the stuff in a list, I'll just type over it. That's what I'll do. But I'll just show you that you could, if I want to get rid of this list 3, go up on top, and I think if I press clear, it clears it out. Okay? But I'm just going to type over. So in list 1, it says the random variable x represents the number of households among 6 that are tuned to 60 minutes during the time the show is broadcast. All right. So what they do is every time they broadcast, they call 6 houses. And then they just see how many of you are watching. They just call, and they say, how many of you guys are watching? Are you watching 60 Minutes? And it's a yes or no question. It's a very simple phone survey. All right? Now, what could happen? Could be that nobody's watching 60 Minutes. How often does that happen? More than half the time. 53%, 53.9% of the time. Do you guys see that? Tyrone, you look confused. Having trouble seeing. I wonder if there's anything I can do. I guess what I could do is I could do it on Excel so you can see the data. Let's do that. So I'll use Excel, and I'll zoom. Yeah, we'll zoom to 400% was the maximum I could do. All right, I'll do it on Excel. Doesn't have to be on a calculator. Okay. So I'm just getting this right out of the book, right? You guys with me? So we had 0, 1, 2, 3, 4, 5, 6. I guess I can make it a tiny bit smaller. Okay, so there's everything. And then we have the data. Let's see, where is it? So most of the time, it says 53.9% of the time, nobody's watching 60 Minutes. Now, sometimes one house is watching 60 Minutes. How often does that happen? Okay, 0.351. Sometimes two houses are watching. How often? 9.5%. 1% of the time, 60 Minutes people are happy. Because three of them, half of them are watching. Half the people they call. How often is 0.00, I'm sorry. I screwed that up. Here's 0.001 for the 4%. And then these, it says 0 plus. But what they're saying is, it almost never happens that all 5 or all 6 are watching. I mean, it's ridiculously rare. Okay. So that's their data. Now, if we want to do things like compute the mean, well, now we have a formula where we could do it. We could say that this is bless you. This guy times this guy. Of course, you're not going to be able to do that on the calculator now, so let me think. You guys see how there's two formulas for variance? We had that last time. The first formula is easier to understand because it looks more like the formula that I taught you originally, but it's harder to compute with. This formula is actually easier to do your computations. Okay? So, if I wanted to say compute the variance, well, let me go back to the Excel spreadsheet. And I'm going to zoom out just a little bit because we're too close. Make it 300%. Okay. And let me label things so you can see what's going on. Okay, what's this column? X. What's this column? Probability of X. What's this column? X times the probability of X. Great. Now, what about this column? Well, I guess if I were going to find the mean, I'll do the mean down here. The mean would be, I just add up these things. So let me write equals the sum of these things. So there's the mean. What's that say? The mean is 0.587. So what's that? Somehow that's the average. That's the expected value of X. Let me write that down. Instead of mean, I will use this notation that we've been using in the book, E of X. The expected value, what does X represent again? Number of what? Number of houses watching what? 60 Minutes. Okay, and I could really make that big if you want to see it. It's the number of houses watching, right? So when I say E of X, what does that mean? That's the expected number of houses watching 60 Minutes. When we call 6 houses during 60 Minutes, how many houses do we expect to be watching? 0.587? So you have to understand what the mean tells you. It tells you that usually, or on the average somehow, less than one house is watching. You've heard this before. Do you guys know what the average number of kids is that people have in the United States? You heard 2.5. I heard 1 point something.
Well, maybe it's one.
But whatever it is, it's a decimal, right? They're not talking about Siamese twins or something where you no. When they say 2.5 kids, they're saying a lot of people have 1 or 2 kids and some people have more. And if you compute the mean in the way I just did, you get a decimal. Does that make sense? That's what we just did. Why would the answer be less than 1? Well, because look, more than half the time, what happens? You get 0. Does that make sense? Yes, David.
This is just the variance.
No, this is just the mean, the expected value. We didn't do the variance yet. Yeah. So what are we going to do about this variance? Well, let's look at the formula again. Which one should we use? Shortcut. Shortcuts are good. What are we going to compute? Well, instead of doing x times p of x in parentheses, what do they say to do? X squared times p of x, right? X squared means what? What does that mean you're supposed to do? X times x, right? So watch what we're going to do. I go to the Excel screen, again, so we can see what's happening. I'm going to make a new column. And it's going to be x. You guys know what caret means, right? That means you raise it to a power. So this is x squared times p of x. You can do this exact same thing on your calculator. And I'll show you that in a second. But x squared times p of x is what I'm going to do here. So I'm going to do equals the first column squared times the second column. Now that's 0 because 0 squared is 0. But if you copy the formula all the way through, there's your x squared times p of x. We'll go back to the calculator and do the same thing. Here's my lists. I did x and I was typing in p of x. So I have 0.539, 0.3, 0.351, 0.19, 0.042, 0.00, oops, 004, and then the others are zeros. Okay? So now what you can do is you can go to L3, and you could say, I want to do a column for x squared times p of x. What's that? Oh, you're right. I screwed up. Thank you. Otherwise, we're going to get the wrong answer. Do you guys see what Shelley pointed out? I did column C by accident, and I don't want that. Thank you, Shelley. Where's my TI-83? Come back. There we are. So I wanted this, but then what I want here, 0.095, because that's what the book had. And then it had 0.014. Yeah, and then this was only 0.001. Oh. Yeah, it's column 2. List 2 should go in column 2. Okay, now I'm ready. So I'm going to try and get column D here. And the way I do it is I go on top of L3. And a lot of you guys have been saying, I can't use the calculator. Well, this is what I'm trying to show you right now, right? So I have 2 lists. And you may not have them in yours. That's okay. But watch. If I want to do something to those lists, I can do it by going up to the name of the list. So list 3 up here, if I press enter, where's my cursor go? Right next to the equals, right? So what is it we want to do? we want to square the x's. What column are the x's in? The x's are in list 1. How do I get list 1? If you hit the second key and then hit the number 1 on your calculator, that types L1. Now what do I want to do to each of those x's? There's an x squared key right here that'll square them. And then I want to multiply, I'll put times what? L2. So let me hit second L2. Where is that? Number 2. Enter. There they are. Okay? Well, we're not quite there yet. That's still not the variance. We're almost there. What's the formula say? It says after you do the x squareds times the p of x's, what are you supposed to do? What's that mean to do? Add them up. And when I'm all done, I'm going to subtract what? Mu squared. Good thing I have the mean already. Wow. Okay. So I'll do it on Excel, and then we'll go to the calculator. So on Excel, let me do this. I'm going to compute the sum. So the sum, I say, equals the sum of what? Of these guys, right? So that was the sum of those guys. And then I have to subtract. So to get the variance, what do I have to do? I take this guy, so I say equals this sum minus, what do I have to subtract? The mean squared. So how do we do squared? I put caret 2. So there's the variance. 0.52 is the variance of this data. 0.528. Now one last thing, and then I'll get your question. I'm going to go over it again, but I added up all of these x squared p of x's, and then I have to subtract the mean squared, okay, which I'm going to do again shortly. But let me go back to the Excel. There's one last thing that we often want to find, which is the standard deviation, right? I'll abbreviate it that way. How do I do that? So you take the square root of this guy, the variance, 0.7269. Okay? Okay, question, David. You've been waiting patiently. Thank you.
For the sum, you add up column
That sum was, we added up, yeah, because in the formula it says we have to add up all the x squared times p of x's. That's right.
and then the variance.
So then the variance was, we took that and we subtracted the mean squared. And that came from this formula here. Okay? And then, of course, standard deviation would be take the square root. So back to Excel for a moment. This third column here, that was x times p of x. When do you add up x times p of x's? If you're trying to get the mean, the expected value. Oh, the calculator, yeah. So how am I going to do that? Let me think of what to do. So back here, we have all our lists, right? Let me try something here. The trick is, how do you get a big sum, right? So if I hit, here's one way to do it. Second quit. and I could hit second list. No, that's not what I want. Sorry. I just want to hit stat. So the second quit, hit the stat button. We want to calculate. Yeah, and here it is. One variable stats. We did that before. But I want to do them this time on list 3. You might say, why are you doing the one variable stats on list 3? Well, I guess what I was looking at is the sum of the x's is 0.873, and that was something I needed. Yeah, I don't like that as well. I mean, it's a way of getting the number, but I think this is easier on a computer than a calculator. I really do. Well, wait a minute. Wait. You're talking test. Okay, now hold on a second. Guys, I want to talk about problem 30 from this section. It says we're going to talk about expected value for life insurance. By the way, when you read expected value, that's the same as what? The mean. And it means that you could look on your little formula card, and there's a formula. So the expected value, the expected value of x is sigma, which means add them up. What is it we add up? X times P of x, okay? That's the formula. Yeah, that's another one from the homework. Problem 30. And so what did they say? They say there is a 0.9968 probability that a randomly selected 50-year-old female lives through the year. You can look that up on the website. They have that data. So let's see. Probability that the female lives through the year equals 0.9968. By the way, I am trying to show you how to be successful with these problems. Do you notice how much I'm writing down? Sometimes I look at homework and I just see an answer and I say, oh, that's when I start putting the 2 instead of the plus, because I say, I'm not sure they understand it. This is demonstrating to me that, oh, this guy read this and they knew there's a formula involved, okay? So I'll show you a couple things. So on your exam next week, if you're doing a problem like this, show me the formula that you think is involved. Show me some of the facts that you've read. Okay. A Fidelity Life Insurance Company charges $226 for ensuring that the female will live through the year. If she does not survive the year, the policy pays out $50,000 as a death benefit. Okay, so let's see. 220 what? $26. That's a fee. And we have a $50,000 policy. Okay. So it says, from the perspective of the 50-year-old female, what are the values corresponding to the 2 events of surviving the year and not surviving? All right. So part A, if she survives, which we hope, right? We hope. Then we could say x equals, how about this? Negative 226, where x, that's the amount of money she makes. Right? She doesn't make any money from life insurance unless she dies. Right? Well, we're hoping she's not going to. It's going to cost her $226. So I'm calling that negative because she paid it out. You could go positive if you wanted, but it said from her point of view. So I thought this is what they meant. If I have it backwards, all that's wrong is my sign. Everything's going to be fine though. Jim, you have a question before I go on?
Yeah, I just wanted to clarify, I guess. You say expected value, that is meaning something that's like, say, mu, right?
Yes, it's also mu.
Would we just say it because, like, I don't know what's really the difference? I mean,
There's no difference. There is no numerical difference. It's two different words that are used for the same thing. So I'm going to use them for the same thing also. Because people will say, like I said before, what do you expect to happen? And they compute this statistic called the expected value. It's just another name. It's also called the mean. I don't know. I don't know what else to say other than that. Okay? So that's what, oh, there's another thing that could happen. If she dies, what does X equal? Well, okay, I guess the family takes in, oh, right, 50,000 minus, yeah, you have to pay the 226 no matter what, don't you? So what would X equal then? It looks like 49,774, right? So that's part A. They wanted me to come up with the two values. Okay. Part B. If a female purchases the policy, what is her expected value? Now remember, here's the formula in the oval here. So what I have here is I have my X's, right? What else do I need if I'm going to use this formula? I need the probability of these things happening. And I have the probability that she survives. What is it? 0.9968. So I guess I could also get the probability that she dies. How would I do that? 1 minus 0.9968 would be 0.0032. So she's probably not going to die, and that's good. We don't want a 50-year-old woman dying. But there it is, right? Okay. So again, my X values were negative 226 and positive 49,774. That's my X values. My P of X values are here. What do I want to do now? I want X times P of X. So I'll make a column for that. And then what am I going to do? Add those up, right? And that'll be the expected value of X. Is that okay? Well, what's the formula say to do? We need to add up the X times P of X's. And that'll be the mean or expected value. That's right. So let's see. Where are we? I need my calculator. Let me clear it out. Okay, so I'm going to do negative 226 times 0.9968. Negative 225.2768. Back to the calculator. I'm going to do positive 49,774 times 0.0032. Enter. 159 point whatever it was. Okay. If I add these, that would give you the expected value. Okay? So if I want to do it quickly, I'll take the answer I just had. Oh, that didn't work. well, here we go. Negative 225 plus 159. I just noticed something. Notice both of them say 0.2768. One of them's negative, one of them's positive. Those are going to cancel each other out. So if you added those together, your answer is going to be negative 66. Yeah, that's the expected value. Now wait a minute. What does that actually say? This is important, right? We want to know the meaning of things. Computing, it's one thing. What does it actually say? Somehow the average is negative $66. Does that mean she's going to lose $66? No, what's probably going to happen? She's going to lose $226. Right? That's what's probably going to happen. What this tells you is how the insurance company stays in business. Because you could argue, hey, what if a couple people die? That insurance company is going to lose a lot of money. And you're right. But the insurance company stays in business because lots and lots and lots and lots of people buy life insurance. And again, we have this law, the law of large numbers, which says that if you have a whole lot of data, the data starts to match the probability. So on the average, yeah, there's a few people that die and the life insurance pays $50,000. But on the average, it's kind of like everybody's paying the life insurance company $66 a year. That's what this means. Is it actually true that anyone's paying $66 a year? No. But that's the average, that's the mean, and it's also called the expected value. Does it make sense?